In computing, online analytical processing, or OLAP, is an approach to answering multidimensional analytical queries swiftly. OLAP is part of the broader category of business intelligence, which also encompasses relational database, report writing and data mining. Typical applications of OLAP include business reporting for sales, marketing, management reporting, business process management, budgeting and forecasting, financial reporting and similar areas, with new applications coming up, such as agriculture. The term OLAP was created as a slight modification of the traditional database term online transaction processing. OLAP tools enable users to analyze multidimensional data interactively from multiple perspectives. OLAP consists of three basic analytical operations: consolidation, drill down, and slicing and dicing. Consolidation involves the aggregation of data that can be accumulated and computed in one or more dimensions. For example, all sales offices are rolled up to the sales department or sales division to anticipate sales trends. By contrast, the drill down is a technique that allows users to navigate through the details. For instance, users can view the sales by individual products that make up a region unregistered trademark S sales. Slicing and dicing is a feature whereby users can take out a specific set of data of the OLAP cube and view the slices from different viewpoints. Databases configured for OLAP use a multidimensional data model, allowing for complex analytical and ad hoc queries with a rapid execution time. They borrow aspects of navigational databases, hierarchical databases and relational databases. Overview of OLAP systems. Core of any OLAP system is an OLAP cube. It consists of numeric facts called measures which are categorized by dimensions. The measures are placed at the intersections of the hypercube, which is spanned by the dimensions as a vector space. The usual interface to manipulate an OLAP cube is a matrix interface like pivot tables in a spreadsheet program, which performs projection operations along the dimensions, such as aggregation or averaging. The cube metadata is typically created from a star schema or snowflake schema or fact constellation of tables in a relational database. Measures are derived from the records in the fact table and dimensions are derived from the dimension tables. Each measure can be thought of as having a set of labels, or metadata associated with it. A dimension is what describes these labels. It provides information about the measure. A simple example would be a cube that contains a store's sales as a measure, and date-time as a dimension. Each sale has a date-time label that describes more about that sale. For example, sales fact table, sale amount time id, time dimension, 2008.101234 time id timestamp, +1234 20,080,902 1235 and 43 seconds, Multidimensional databases. Multidimensional structure is defined as a OLA variation of the relational model that uses multidimensional structures to organize data and express the relationships between data. The structure is broken into cubes and the cubes are able to store and access data within the confines of each cube. Each cell within a multidimensional structure contains aggregated data related to elements along each of its dimensions. Even when data is manipulated, it remains easy to access and continues to constitute a compact database format. The data still remains interrelated. Multidimensional structure is quite popular for analytical databases that use online analytical processing applications. Analytical databases use these databases because of their ability to deliver answers to complex business queries swiftly. Data can be viewed from different angles, which gives a broader perspective of a problem unlike other models. Aggregations. It has been claimed that for complex queries OLAP cubes can produce an answer in around 0.1% of the time required for the same query on OLTP relational data. The most important mechanism in OLAP which allows it to achieve such performance is the use of aggregations. Aggregations are built from the fact table by changing the granularity on specific dimensions and aggregating up data along these dimensions. The number of possible aggregations is determined by every possible combination of dimension granularities. The combination of all possible aggregations in the base data contains the answers to every query which can be answered from the data. Because usually there are many aggregations that can be calculated, often only a predetermined number are fully calculated. The remainder are solved on demand. The problem of deciding which aggregations to calculate is known as the view selection problem. View selection can be constrained by the total size of the selected set of aggregations, the time to update them from changes in the base data, or both. The objective of view selection is typically to minimize the average time to answer OLAP queries, although some studies also minimize the update time. View selection is NP-complete. Many approaches to the problem have been explored, including greedy algorithms, randomized search, genetic algorithms and a search algorithm. Types: OLAP systems have been traditionally categorized using the following taxonomy. Multidimensional. MOLAP is a multidimensional online analytical processing. MOLAP is the classic form of OLAP and is sometimes referred to as just OLAP. MOLAP stores this data in an optimized multidimensional array storage, rather than in a relational database. Therefore it requires the pre-computation and storage of information in the cube, the operation known as processing. MOLAP tools generally utilize a pre-calculated data set referred to as a data cube. The data cube contains all the possible answers to a given range of questions. MOLAP tools have a very fast response time and the ability to quickly write back data into the data set. Advantages of MOLAP: fast query performance due to optimized storage, multidimensional indexing and caching. Smaller on-disk size of data compared to data stored in relational database due to compression techniques. Automated computation of higher-level aggregates of the data. It is very compact for low-dimension data sets. Array models provide natural indexing. Effective data extraction achieved through the pre-structuring of aggregated data. Disadvantages of MOLAP: within some MOLAP solutions the processing step can be quite lengthy, especially on large data volumes. This is usually remedied by doing only incremental processing, that is, processing only the data which have changed instead of reprocessing the entire data set. MOLAP tools traditionally have difficulty querying models with dimensions with very high cardinality. Some MOLAP products have difficulty updating and querying models with more than 10 dimensions. This limit differs depending on the complexity and cardinality of the dimensions in question. It also depends on the number of facts or measures stored. Other MOLAP products can handle hundreds of dimensions. Some MOLAP methodologies introduce data redundancy. Relational. OLAP works directly with relational databases. The base data and the dimension tables are stored as relational tables and new tables are created to hold the aggregated information. It depends on a specialized schema design. This methodology relies on manipulating the data stored in the relational database to give the appearance of traditional OLAP slicing and dicing functionality. In essence, each action of slicing and dicing is equivalent to adding a where clause in the SQL statement. Our OLAP tools do not use pre-calculated data cubes but instead pose the query to the standard relational database and its tables in order to bring back the data required to answer the question. Our OLAP tools feature the ability to ask any question because the methodology does not limit to the contents of the cube. Our OLAP also has the ability to drill down to the lowest level of detail in the database. Hybrid. There is no clear agreement across the industry as to what constitutes hybrid OLAP, except that a database will divide data between relational and specialized storage. For example, for some vendors, a OLAP database will use relational tables to hold the larger quantities of detailed data, and use specialized storage for at least some aspects of the smaller quantities of more aggregate or less detailed data. OLAP addresses the shortcomings of MOLAP and OLAP by combining the capabilities of both approaches. OLAP tools can utilize both pre-calculated cubes and relational data sources. Comparison. Each type has certain benefits, although there is disagreement about the specifics of the benefits between providers. Some OLAP implementations are prone to database explosion, a phenomenon causing vast amounts of storage space to be used by OLAP databases when certain common conditions are met: high number of dimensions, pre-calculated results and sparse multidimensional data. OLAP generally delivers better performance due to specialized indexing and storage optimizations. OLAP also needs less storage space compared to OLAP because the specialized storage typically includes compression techniques. OLAP is generally more scalable. However, large volume pre-processing is difficult to implement efficiently, so it is frequently skipped. OLAP query performance can therefore suffer tremendously. Since OLAP relies more on the database to perform calculations, it has more limitations in the specialized functions it can use. OLAP encompasses a range of solutions that attempt to mix the best of OLAP and MOLAP. It can generally pre-process swiftly, scale well, and offer good function support. Other types. The following acronyms are also sometimes used, although they are not as widespread as the ones above: WOLAP, Web-based OLAP, DOLAP, Desktop OLAP, RTOLAP, Real-time OLAP, APIs and query languages. Unlike relational databases, which had SQL as the standard query language, and widespread APIs such as ODBC, JDBC and OLEDB, there was no such unification in the OLAP world for a long time. The first real standard API was OLTP for OLAP specification from Microsoft, which appeared in 1997 and introduced the MDX query language. Several OLAP vendors, both server and client, adopted it. In 2001, Microsoft and Hyperion announced the XML for Analysis specification, which was endorsed by most of the OLAP vendors. Since this also used MDX as a query language, MDX became the de facto standard. Since September 2011, LINQ can be used to query SSAS OLAP cubes from Microsoft.NET. Products. History. The first product that performed OLAP queries was Express, which was released in 1970. However, the term did not appear until 1993 when it was coined by Edgar F. Code, who has been described as the father of the relational database. Code's paper resulted from a short consulting assignment which Code undertook for former Arbor Software, as a sort of marketing coup. The company had released its own OLAP product, Essbase, a year earlier. As a result, Code's 12 laws of online analytical processing were explicit in their reference to Essbase. There was some ensuing controversy, and when Computer World learned that Code was paid by Arbor, it retracted the article. OLAP market experienced strong growth in late 90s with dozens of commercial products going into market. In 1998, Microsoft released its first OLAP server, Microsoft Analysis Services, which drove wide adoption of OLAP technology and moved it into mainstream. Product comparison. Market structure. Below is a list of top OLAP vendors in 2006, with figures in millions of US dollars. See also: data warehouse, online transaction processing, business analytics, predictive analytics, comparison of OLAP servers, data mining, Thomson diagrams, bibliography, Daniel Lemire. Data warehousing and OLAP: a research-oriented bibliography. Eric Thomson. OLAP Solutions, Building Multidimensional Information Systems, 2nd edition. John Wiley & Sons. ISBN A978-0-471-14931-6. Ling Liu and Tamer M. Azu. Encyclopedia of Database Systems, 4100 PA 60 LS. ISBN 978-0-387-49616-0. O unregistered trademark Brian, J.A., and Maracas, GM Management Information Systems. Boston, Massachusetts, McGraw-Hill Irwin. References